Welcome to this lecture on Solutions of Exercise 6.4, Question 14 to Question 18 by Dr. Rajesh Singh.
Welcome everyone. Today we are going to solve exercise for section 6.4 from the book Bartle and Sherbert. So in previous videos we have solved from question number 1 to question number 13. So in this video we will solve from question number 14 to question number 18. Let us start with the first question, which is question number 14. So in this question we are asked to determine whether the point x equal to 0 is a relative point of extrema of the following functions or not. So for this we are going to use the relative extrema theorem which we did. This is the theorem that we are going to use. So according to this, so basically what we are going to do is we will keep on finding the derivatives at x equal to 0, all the derivatives at x equal to 0, provided until we get the first derivative which is non-zero. This is what we are going to do. So we'll continue to find derivatives unless we get a non-zero derivative at 0. So let us start. So let us take the first part, which is A. So let us start with part A. A is fx equal to x cube plus 2. So basically our aim is to find the smallest n such that fn is not equal to 0. So first we will find this and then we will apply this theorem to get our result. So f dash x is 3x square. So f dash 0 is non-zero. Oh, sorry, is 0. F dash 0 is 0. So we will continue and we will find the second derivative f double dash x, which is 6x, and f double dash 0 is also 0. So we'll find the third derivative. F triple dash x is 6. So f triple dash 0 is non-zero. So the smallest higher order derivative which is non-zero is third derivative. And because it is odd, so f has neither a relative minimum nor relative maximum at x equal to 0. So by higher order derivative test, f does not have relative extrema at x equal to 0. Now let us take the part B. So P is gx equal to sin x minus x. So gx equal to sin x minus x. So again we will find the first derivative, which is cos x minus 1. So g dash 0 is, so cos 0 is 1. So 1 minus 1, which is equal to 0. So first derivative is 0. Now we will find the second derivative, g dash x, which is minus sin x, and g double dash 0 is sin 0, which is 0. So now we will find the third derivative, g triple dash x, which is equal to minus cos x, and so g triple dash 0 is equal to minus 1, which is non-zero. So again in this case g does not have relative extrema at x equal to 0 because this is odd. So again by higher order derivative test, higher order derivative test does not have relative extrema at x equal to 0. Now let us take the third part, the C part. So we are given hx equal to sin x plus 1 by 6 x cube. So hx equal to sin x plus 1 by 6 x cube. So h dash x is cos x plus 3x square by 6. So h dash 0 will be, so h dash 0 is 1, which is non-zero. So again it is non-zero at odd derivative. So this by higher order derivative test, h does not have relative extrema at x equal to 0. Now let us take the fourth part, the d part. So kx is equal to cos x minus 1 plus 1 by 2 x square. Kx equal to cos x minus 1 plus 1 by 2. Now finally let us find the derivative. So k dash x is minus sine x plus x. So k dash 0 is minus sine minus 0 plus 0, which is equal to 0. So first derivative is 0, so we will find the second derivative. So it is minus cos x plus 1. So k double dash 0 is again 0, so we will find the third derivative. So it is third derivative is sine x. So k triple dash 0 is 0, so we'll find the fourth derivative. So fourth derivative is cos x. So k40 is equal to 1, which is non-zero. So by higher order test, and it is positive. It is positive. It is strictly greater than 0. And this is even. So by higher order derivative test, k has relative minima at x equal to 0. And if you see, k0 is cos 0 minus 1 plus 1 by 2 x square. So this is cos 0 is 1 minus 1, so 1 by 2. It is 1 minus 1, which is equal to 0. So 0 is the minimum value. 0 is the minimum value of k. Okay, now let us take, so that we have completed question number 14. Now let us take the question number 15. So in question number 15, we are given a continuous function which is continuous on closed interval AB, and we are assuming that its second derivative exists on the open interval AB. We also suppose that the graph of f and the line segment joining the points AFA and BFB intersects at a point x0 fx0 where A is less than x0 less than B. Show that there exists a point C belonging to AB such that the double derivative at that point is 0. So we have to find a point at which the double derivative of the function is 0. So basically if you look at this, so it is, so we are given some function. So we are given some function. So this is B. This you can take it as A. I'll make it a little curve. So this you can take it as A. This is B. This is AFA. This is BFB. And so this is the line joining AFA and BFB. And this is the point. So it intersects the curve at the point x0 fx0. So this is the point x0 fx0. So fx0 is here. So we have to show that there exists some point in the open interval AB such that the double derivative of the point is equal to 0. So what we will do is we will apply, because the function we will apply mean value theorem to now. So we will apply mean value theorem to functions on this interval a to x0 and x0 to b, and then we will use the property, one of the properties. Let us see. Let us start with this proof. So because f is given to be continuous on closed interval AB and our double derivative exists, so that means f dash is also existing. So since f is continuous on closed interval AB and f is differentiable because it is given that double derivative exists, so that means f is also differentiable on open interval AB. So by mean value theorem, there exists C1 and C2, C1 lying between C1 belonging to A to x0 and C2 belonging to x0 to B, such that f dash C1 is equal to fx0 minus fa upon x0 minus a, and f dash C2 is equal to fb minus fx0 upon x0 minus b. And now since fx0 minus fa upon x0 minus a and fb minus fx0 upon x0 minus b is, yeah, or we can say since, because if the slope of this line, so slope of line segment joining AFA and BFB is given by, is equal to, so because these are points on the line, so we can have this is also slope of the line and this is also the slope of the line segment joining the points AFA BFB. So these two are equal, so that implies f dash C1 is equal to f dash C2. So this implies f dash C1 is equal to f dash C2. So applying, so then f dash is continuous on closed interval C1 to C2 and f dash is differentiable because double derivative exists C1 to C2. So by also f dash C1 is equal to f dash C2. So by Rolle's theorem, there exists C lying between C1 C2 such that f double dash C is equal to 0, the derivative of this. So that implies since C1 C2 is contained in AB, so this implies there exists C belonging to AB such that f double dash C is equal to 0. Hence proved. So basically what we have done in this question is, first we have applied mean value theorem to the interval a to x0 and to the interval x0 to b, or to f on the interval a to x0 and x0 to b. So we got these two derivatives, and then we observed that this and this both are slope of this line, and because this line is same, so both the slopes are equal. So the slopes are equal, so that means this derivative and this derivative is equal. So now we apply Rolle's theorem to the function f dash on the interval c1 to c2 to get our desired result. So this completes question number 15. Now let us move to question number 16. So question number 16 is again a very simple question. You just start with double derivative, applied the limit definition of derivative to get this formula. So let us start the solution. So we will start with f double dash. It's simple. So we will apply the limit derivative formula. So this is f dash a minus f dash a minus h. Basically change in a upon h. So this is the formula for derivative. Then again apply this formula. So now we want, so now apply to this. So this is limit h tends to 0, f of a plus h minus f of a upon h. Again apply to this, so there will be change, so we can have like this, f of a minus f of a minus h. So in this case we are adding, or let us just move this slightly on this side so that we can write it properly. Okay, so this is f of a minus h upon h. Now you can take the limit outside and just organize this, so you will get, see, so the fa becomes 2fa, so you just get the desired formula. So f of a plus h minus 2fa plus f of a minus h upon h square, and you can take this limit h tends to 0 outside and you can club it with this because h is tending to 0 anyway. So we get the desired formula. Okay, so this completes question number 16. Now let us move to question number. Okay, so there is one more thing in question number 16. So we have to give an example where this limit exists, but the function does not have a second derivative at a. So this is also there in this question number 16. This thing, paste it. So we also have to give an example where this limit exists, but the function does not have a second derivative at a. So this limit exists, but we will show that it is not, if second derivative does not exist at that point. So let us give the example. Example is the function that we have done in one of our classes. So it is the function fx equal to, you all have seen this function, x square sine 1 by x if x is not equal to 0, and 0 if x is equal to 0. So we know about this function that its derivative exists at every point, but the derivative is not continuous and hence cannot be differentiable. So we are going to use that fact. So first we observe that this limit exists. So we will work at this. So a equal to 0. So f of a plus h minus 2fa plus f of a minus h by h is equal to h square. So this is equal to f of h minus 2f0 plus f of minus h upon h square. So this is h square sine 1 by h minus 0 plus h square sine minus 1 by h by h square. Now sine minus 1 by h is minus sine 1 by h. So these two terms will cancel out each other and you will have 0 by h square, which is equal to 0. So when you will take the limit h tends to 0, f of a plus h minus twice of f a plus f of a minus h by h square. So you will get limit h tends to 0, 0. So this is equal to 0. Hence limit exists. Now let us show that double derivative of f at 0 does not exist. So for that, observe that f dash x, f dash 0, we know that f dash x is, so you can easily check it out. F dash x is, so just differentiate this, you will get for x not equal to 0, it will be 2x sine 1 by x and then minus plus x square cos 1 by x into minus x square. So it is, you will get minus cos 1 by x when x is not equal to 0, and for x equal to 0 you can easily calculate using the limit formula. So limit x tends to 0, fx minus f0 by x minus 0. So this is limit x tends to 0, x square sine 1 by x. So this is limit x tends to 0, x sine 1 by x, which is equal to 0. So f dash 0 is 0 when x is equal to 0. Now this function is not continuous at x equal to 0. It is easy to see. So the function f dash is not continuous at x equal to 0 and hence f double dash 0 does not exist. So we are able to show that although limit exists, this limit exists, but the function is double derivative does not exist. So if the double derivative exists, then it has to be equal to this limit, but this limit can exist without double derivative being into existence. So this completes question number 16. Now let us move to question number 17. So in question number 17, we are given an open interval I, and we are also given that the double derivative is positive on the open interval I. For any point C belonging to I, we have to show that the part of the graph of f on I is never below the tangent line to the graph at CFC. So basically what it means is that our graph is of this form. So graph is always of this form. So this is the tangent. So this is the point CFC. So tangent is always below the graph. So what, or let me just show you. So this situation is not there. Basically this situation is not there. So we have to show that this situation is there. That is what we have to show basically is, if you look at this, so we have to show that our at point C belonging to I, so this is some C, this is tangent at C, FC. So we have to show that this. So for any point in this neighborhood in around C, so if we pick any point around X, any point X, so that means our Fx, so this is Fx, and this is the image of X on the line. So this Fx should be greater than this point. So that is what we have to show. So if the equation of this line is gx, and if the equation of this line is fx, so basically we have to show that fx is greater than or equal to gx. Gx is the equation of the line. Okay, so this is what we have to show. So equation of the tangent is equation of tangent to f at c fc is given by, so slope point form we will use. So CFC is the point and slope is f dash c. So it will be, so slope point form, so y minus fc upon x minus c is equal to f dash c. So y is equal to fc plus y is equal to fc plus f dash c x minus c. So now to prove, this is the equation of the tangent to the curve f at c. So we have to basically show that our fx is greater than or equal to y. So that means we have to show that fx is greater than or equal to this, because what we are asked is, we are asked the part of the graph of f on I is never below the tangent line to the curve at CFC. So basically we have to show that our fx is greater than or equal to y. So now claim fx is greater than or equal to fc plus f dash c x minus c for every x in I. So this is what we need to show to prove this theorem. To prove this this example, part of the graph of f is never below the tangent line. So this is what we need to show. So what we will do is we will apply Taylor's theorem for this at c. So because it is x minus c, and since it is the first derivative, so we will take n equal to 1. So that x naught equal to c using x naught equal to c, and for any x belonging to I by Taylor's theorem for n equal to 1. So we are using Taylor's theorem for n equal to 1. So what we will have is fx is equal to fc plus f dash c x minus c plus f double dash c x minus c square by 2 factorial. Now if you see this, that now this double derivative is given to be positive, and this is square, so this is positive, and so this term is positive, so which is greater than equal to fc plus f dash c x minus c, since f double dash x is c is positive, because we are given that derivative is positive. Okay, then so this c is different. This c is different. This c lies between c and x, so we can write it as d. Okay, so there exists d lying between c and x such that now f dash, because we are given the derivative is positive everywhere on I, so f double dash d is positive. Okay, so this is given to us, given fact. So hence our fx is greater than equal to fc. Hence proved. So this is question. So this completes question number 17. Now let us move to question number 18, which is the last question that we are going to do today. Again, this question is a simple application of Taylor's theorem. So in this question, we are given an interval I and C is any point in I. We are given two functions f and g defined on I such that fn and gn exist and are continuous on I. We are also given that fkc is equal to 0 and gkc is equal to 0 for k equal to 0 to n minus 1. So that means fc is 0, f dash c is 0, f double dash c is 0, and fn minus 1c is also 0. And we are also given that g0 is 0, g dash c is 0, and up to gn minus 1 is 0. But we are also given that gnc is not equal to 0. So what we will do is we will apply first Taylor's theorem to f and Taylor's theorem to g, and then we will take the limit and use the continuity of fn and gn to get this desired result. So let us start. So because we want to use at c, so let x naught equal to c, and for any x belonging to I, by Taylor's theorem there exist d1 and d2 lying between c and x such that fx is equal to f0 plus f dash 0, sorry, fc, because x naught is equal to c, so fc plus f dash c x minus c plus f double dash c x minus c square by 2 factorial plus, so we will apply till n minus 1, so and we are taking up to n minus 1 basically, so fn minus 1c x minus c to the power n minus 1 by n minus 1 factorial, and then remainder after n terms, so the rn minus 1. So this is fn c, so this will be d, so fn d1 x minus c to the power n by n factorial, and similarly gx will be g of c plus g dash c x minus c plus so on gn minus 1c x minus c to the power n minus 1 by n minus 1 factorial, and the remainder after n terms, so this is gn d2, so these two are different, d1 d2 are different, and they lie between x and c, they lie between c and x, x minus c to the power n by n factorial. So since fc equal to f dash c equal to fn minus 1c is equal to 0, and gc equal to g dash c equal to this, it is given to us gn minus 1c is equal to 0, so we get fx, so all the terms with all these terms are 0, all these terms, this is 0, this is 0, all these terms are 0, so we will be only left with remainder. And again here all these terms are 0, so we will be left with remainder. So fx is equal to fn d1 x minus c to the power n by n factorial, and gx is equal to fn d2 x minus c to the power n by n factorial. Now, because d1 and d2 lie between x and c, and we need to find limit x tends to c, so that means our d1 and d2 are very close to c. So since g and c is not equal to 0, so we can assume that our g and d2 is also not equal to 0. Or what we can do is we can find the limit. So limit x tends to c, fx is equal to, we have to find, we cannot find the limit first, otherwise it will become 0. So divide fx, so sorry, this is g and d2. Now GNC is not equal to 0 and GN is continuous on I. Now GNC is not equal to 0 and GN is continuous on I, so there exists delta neighborhood V delta of C such that GNX is not equal to 0 for all x belonging to V delta neighborhood of C. So for any, now so what we will do is, so for x belonging to V delta of C, we take x to be there fx by gx, fx by jx, because if x belongs to V delta of C, then this d2 will also belong to x delta of C, because V delta of C, because d2 lies between C and x. So then we can divide, because now we are ensured that this is not equal to 0, so we can divide. So we can divide these two terms, so this will be fn d1 upon x minus c by n factorial upon gn d2 x minus cn by n factorial. X belonging to V delta of C implies d2 belongs to V delta of C, and this implies gn d2 is not equal to 0. So then we can divide these two. So after dividing, these two gets cancelled out, so we are left with fx by gx equal to fn d1 by gn d2. Now we will take the limit. So limit x tends to c, fx by gx is equal to limit x tends to c, fn d1 by gn d2. Now because these two are continuous functions, so we can take the limit inside. So limit x tends to c, fx by gx is equal to limit, or we can write like this, fn limit x tends to c d1 and gn limit x tends to c d2. Now since d1 d2 lies between x and c, so x tends to c implies, so x tends to c implies d1 tends to c and d2 also tends to c. So using this they get limit x tends to c fx by gx is equal to, so this will be fnc and this will be gnc. So hence proved. So this much is there in this video. Thank you everyone. Have a good day.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.